G'day viewers. In this segment we'll talk about protocols and layering. This is one of the most important concepts in networking because it describes how the functionality of the network is structured. It's covered in section 1.3 of your text. So, some of the rationale for protocols and layering is that networking needs a form of modularity. We looked at a socket application, and just from that and running your own applications, you know that the network does a great deal for applications. It enables the making and breaking of different connections to send information between them. It delivers the information reliably when you ask for it to be sent. To do all of this in the first place, it needs to find a working path through the network from one host to the other host to which you're trying to speak. It sends information of arbitrary length, even though we'll find out later that only small amounts of information can be put in an individual packet. It sends information as quickly as the network allows, which depends on the path through which you take through the network. It also shares the bandwidth between multiple users. Different numbers of users may be using your path at any particular time as they start and stop watching video, and the network needs to apportion the bandwidth between whoever is trying to use it. And you can see it does some other things here. It secures your information in transit. It also accomplishes all of these things with a design while letting other hosts be added. Hosts can come and go quite easily and so forth. This is a large amount of complexity. The key point here is that what we really need is some form of modularity which will help us manage this complexity and enable us to obtain some reuse out of the different functions which exist inside networks. Here we are. Protocols and layering are the structuring method which is used in networks to divide functionality up into smaller pieces which can then be reused. The way they work is as follows. Each instance of a protocol is able to talk virtually to the corresponding instance of the protocol, called a peer, on a different host elsewhere in the network. To do this, the instance of the protocol uses only the services of the lower layer which sits on the same host. Let me just draw a picture of that to work through some of the concepts. Okay, so here is an instance of a protocol. We'll call it protocol X. That's going to be running on some host. So there's some host here. It will talk virtually to a peer instance of protocol X. I'm going to make dots to show that it will talk virtually, because in fact, this protocol X can't reach the other peer instance of protocol X directly. The way it will talk is it will actually use the services of a lower layer, protocol Y, who will somehow promise to get information to protocol X on the other side of the network. And this is in a different host. So these boxes are protocols. These are two different layers. This is layer X, and this is layer Y. Let me just clean up that picture as follows. So one thing that is important to take away here is that protocols on this picture are horizontal interfaces. So protocol actions take place between two peers which are horizontally separated within a layer. Whereas the service interfaces provided from one protocol to another, there are these vertical lines up and down. Protocol X makes use of the service provided by protocol Y, which is its lower layer. Of course, this picture doesn't describe everything yet because we haven't said how protocol Y virtually communicates with its peer instance of protocol Y. It will clearly do this by using some yet lower layer protocol, which is not shown in this diagram. So let's expand the diagram. Here we are, and you can see we have a whole set of layers that builds on one another. Now the set of protocols in use in a particular node for a particular application is called a protocol stack. And there's no mystery here because at the very bottom, after layer 1, you can see that there's the physical medium. This is really a wire. if you like, is connecting the two layer 1 protocols. At the very bottom, it's the wire that carries the signal, or the wireless that provides that connectivity. The layers are building ever higher layer and more sophisticated forms of communication on top of one another. Now, we've just been talking about protocols in the abstract with Protocol X and Protocol Y, but you've probably heard of many existing protocols already. You've no doubt heard of TCP, IP, 802.11, Ethernet, HTTP, SSL, DNS, and many, many more. You might not have realized at the time, but all of these different acronyms represent different network protocols, and we're going to cover those protocols during this course. I'll just show you an example of them in use to draw a protocol stack. Imagine we have the situation of a web browser which is on a wireless host running to talk to some server across the network. Let's look at the protocol stack that's on that host. So here is the browser. I'll draw the wire out the bottom. The protocol stack will exist in between. Now, I just happen to know what some of the layers in this protocol stack will be. The top layer will be HTTP, the web protocol, which happens to run on top of TCP, which runs on top of IP, which runs on top of, since we said this was a wireless host, 802.11, if it's a Wi-Fi kind of wireless. At this stage, I wouldn't expect you to know why those particular protocols are in use. They just are. During the course, we'll look at all of these protocols and you'll come to understand why these are the protocols that are used. Let me clean that up a bit. Here's a cleaner version of the diagram, just so you can see it more clearly. Now, let's talk about encapsulation. So far, I've talked about protocol stacks and different layers, and said one layer builds on another. But we haven't told you the exact mechanism by which layers build on one another yet. Encapsulation is that mechanism that's used to affect protocol layering. A lower layer wraps a higher layer. It takes the higher layer content and it adds its own information to make a new message for delivery. It can then pass that whole message down to the next lower layer, where it will continue and eventually something will be sent out over the network. This is very much like putting a letter inside an envelope for delivery in the postal service. The envelope wraps your letter. The letter is the contents. The postal service doesn't need to look at the contents of your letter. It only needs to look at information on the envelope to get the letter to the other side. Once it gets to the other side, of course, then you open the envelope, out comes the letter, and the content has been delivered by the network. Now we can draw encapsulation as it happens. Here's an example. We have the protocol stack on the right, our same protocol stack from before, HTTP, TCP, IP, and 802.11. So imagine that the browser, imagine that we start with an HTTP message. Here's a message, I'll write HTTP in it. The HTTP layer will pass that down to TCP. TCP will then encapsulate it by putting that message as the contents inside a packet, and it will add some TCP information of its own to the packet. The TCP layer will then pass this whole package down, where it will be wrapped by the IP layer. The IP layer will add some contents of its own and then pass the whole unit down, where it will be wrapped by the 802.11 layer, encapsulated by the 802.11 layer. I should really be drawing the information that's added by the new layer at the front there. So you can see, I'm going to put IP here and cross it out from there, because I intend to indicate that this whole thing goes down from above and into the packet. So we're wrapping boxes within boxes, if you like. I've cleaned up that diagram here. You can see here as we go down it's the same protocol stack and the same process. Here I've drawn the boxes inside boxes more clearly. I just couldn't provide that level of detail on the previous slide. But so you can see that this HTTP unit is wrapped inside TCP, and then the whole thing again is wrapped inside IP and in 802.11 and so forth. Because of this, the message at the lowest layers and the one which goes out on the wire begins to look somewhat like an onion. There's layer on layer. And note here, it's easy to get confused about this, but you'll note that because these layers have been added when the message goes down the protocol stack, the lower layers are outermost in this wrapping, not innermost. Well, we can draw further pictures. showing encapsulation in action. I've just expanded this picture here in this compound figure. On the left side, I have what I had before, a protocol stack, HTTP, TCP, IP, 802.11, and the encapsulation. That was just one host. So I've shown the wire across the network, and on the right-hand side, the corresponding host. Now the protocols have to match so that a peer is talking to its correct peer instance. You can see what goes out the wire at the bottom is this compound unit, the very lowest layer. So it's that greatly wrapped thing, boxes within boxes. That same message then, after it's gone across the wire, is received on the other side. And on the other side, what the 802.11 layer will do is it will look inside and it will extract the contents, excuse me, which is the IP, the IP contents and everything that's wrapped inside that, and it will pass that up to IP. IP in turn will look inside and take out the TCP and HTTP contents and pass it up to HTTP. Just going to draw the arrows on the other side so you can see it went down this side and up on the other side. And similarly, our last step up. Because of this, you can see that this is how the TCP protocol, if we just pick one in the middle, communicates with its peer instance. TCP really wanted to send this message over to the other side, and it has, by virtue of using this encapsulation mechanism in the protocol stack. Well, for encapsulation, I showed you boxes with inside boxes. That gets old real fast if you're trying to draw it. Normally we draw encapsulation like this. The most common form of encapsulation is when each lower layer adds a small amount of information to the front. So we usually draw it as one simple linear box. If we start with HTTP, here when it's encapsulated, the TCP layer will take the HTTP part as the contents and add its own TCP header. The information that goes to the front is called a header. When it passes it down, IP adds its own header, and similarly 802.11 adds its own header. The leftmost portion here shows the first bits that go out on the wire, the 802.11 bits, and the rightmost side shows the last bits which go out on the wire, and they're the higher layer content. This is a fairly simple representation of a packet. If you look at real packets, you'll see it's a little more involved in practice. Some layers could actually add some what are called trailers as well as headers. This is some of the wrapping which goes around the packet at the end of the packet instead of at the front, but conceptually it's no different. Some layers might actually transform the contents in ways which could be undone at the other side. For instance, you might encrypt or compress the contents. And of course, we might also need or have situations in which a layer passes down a large message, like an HTTP web page, and it doesn't fit within one packet. So it needs one long message from a higher layer needs to be divided into many smaller messages at a lower layer. This is called segmentation on the sending side, and reassembly on the other side when you take all of those small messages and put them back together. Well, we have just one more bit of machinery to understand protocols and layering, and that is demultiplexing. This is looking at the receive side when you get an incoming packet. Now, we usually show you a protocol stack so you know what the packet's going to go through. But you could have many applications running on a host. You might have your web browser running, but you might also have Skype. You might be doing DNS queries, having a voice over IP call, doing anything you like, watching a movie. All of these applications are running concurrently. So when we get a packet in, we need to decide what protocol stack to put it up. This picture shows the complete set of protocols which is running on a host. This is called a protocol graph. It's what you get when you combine all of the different protocol stacks on one host. You can see it's somewhat of a tree because as we go up from a lower layer, there are different possibilities for the higher layer. If this is our packet from before, we know that it should go up this path when the packet is received. From our previous example, it would to go up through Ethernet, IP, TCP, and HTTP. But how do we ensure that it will be routed up that path and not some other path and that we won't confuse packets? Well, the answer is that it's done with demultiplexing keys. When the protocols add their information to the start, they also include a little bit of information which can be used on the receive side to pick the correct upper layer. So here is our same packet, incoming packet coming in, and let's say we just know that it's Ethernet because we only have Ethernet at the lowest layer. Somewhere inside the Ethernet header, there will be a field. I'll just put a dot here for it. In the case of Ethernet, it's called the ether type value, and that will tell the receiving host that the next higher layer is IP. It will have a certain value, so the packet will be passed up to IP rather than to this ARP protocol, which was an alternative. Inside the IP header, there is a field called protocol. If you look at the value of that field, for this packet, we would see that it has a value which means TCP is the next higher layer, and you would pass it up this way rather than to UDP, for instance. And guess what? TCP also has a demultiplexing key. In the case of TCP, it's the port number. The port number will make sure that it is passed to the right port where the web browser lives, and that web browser is implementing the HTTP protocol as part of the code base there. And there we have demultiplexed an incoming packet. Layering has several key advantages. The big advantages that we're getting are information hiding and reuse. Let's just explore that a bit and see an example in action. Okay, here's our friend, the web browser and server. They're both talking over the HTTP protocol, the web protocol. What are the protocols underneath? Well, there are different possibilities. One we've looked at is this. Underneath is TCP, IP, and 802.11. This is when our host was on wireless. Now, because these protocols only talk to peers, we need to have exactly the same thing on the other side. However, there could be a host which is running a web browser on an Ethernet network. In that case, a different set of protocols would be underneath. Actually, the first ones would be the same. It would be TCP and IP and then Ethernet. Because everything is the same in this case except the lowest layer of how they're actually attached to the network. So we're seeing information hiding and reuse here. The hiding part is that the browser and the server don't know and they don't care whether they're running over 802.11 or whether they're running over Ethernet. So we don't have to write a different version of them for these different networking technologies. That information hiding is providing a vast simplification in terms of making manufacturing networks. We're also seeing a lot of reuse here because the same TCP and IP modules are being used whether we're using 802.11 or Ethernet. We don't need different versions because of it. We similarly get to use TCP and IP regardless of whatever's above us. For applications that want to use a stream mode of delivery. Right now it's the web browser, but it could be any other application. Oh, here's a cleaned up version of that diagram, just to make it a little clearer. But let's move on and look at the advantage of layering in terms of information hiding a little more. We can use it to connect different systems. This is more interesting, I think. So here we have a computer, a protocol stack, the same protocol stack as before with wireless at the bottom, and on the right hand side we have one with Ethernet at the bottom. How can we connect these? We can't just connect the wire because the 802.11 protocol only wants to talk to an 802.11 peer instance, and similarly for the Ethernet protocol. So you can't literally put these things together yet. But what we can do is make a box in the middle of the network to which these wires connect. And inside that box, the 802.11 needs to have an 802.11 peer. I'll put that there. This 802.11 peer will terminate the 802.11 layer and pass the information up to the next higher layer. That next higher layer needs to be IP. But instead of going any further up, let's just inside the IP layer, we'll pass the information across to another IP layer. This is really just internally passing a packet across. And then we'll pass it down to an Ethernet layer. As we pass it down to the Ethernet layer will put its own header on it and wrap it in a different way. This will allow, by running the Ethernet protocol, this will allow us to talk to the Ethernet peer instance on the other side. And then we'll proceed up the stack and we've managed to connect two systems running a web browser and a web server, even though they're operating on different kinds of networks. Here's a cleaned up version of that same thing. You can see I've also drawn the packets as they go over the wire and as they go through the middle of that device inside the network. This device, by the way, is actually a router. This is exactly what a router does, something like this. I've also shaded in these packets the portion which is not touched by the device as it goes through the network, so it's delivered through unchanged. And that's the TCP and HTTP portions. The other portions can change. In particular, this 802.11 portion, when we got to the device in the middle of the network, that was taken off and it was replaced with an Ethernet portion. So even though it was sent, it was not received by the other side. It was received by the router and processed appropriately. Similarly, the IP layer, the IP header can change slightly as we go through the IP layer in the network. But the higher layers, the TCP and HTTP, which is shown in a pinkish hue there, are unchanged. Layering has some disadvantages too. It's not all roses, but on the whole, it is a major win. So what are some of the disadvantages? Well, there are two. Layering adds overhead, all of these boxes within boxes, wrapping packets. Now, if you wanted to, if you knew what the protocol stack is, I'm sure you could come up with a more efficient way to wrap it instead of passing things down through all of these layers, and you might save a few bytes. However, these savings tend to be small. The overhead of layering is small for large packets in particular. We're talking about a small number of percent of bytes, most likely. The second disadvantage of layering, and I think this is the more important one, is that layering hides information. Now, that's good in the sense that it's hiding things we mostly don't want to know about, but not always. An application, in fact, might care whether it's running over a wired or a wireless network. They're quite different. In terms of wireless, your bandwidth may vary considerably over time, for instance, and errors can be a more significant issue. So an application might actually want to know what's going on at those lower layers. Layering hides this information from us so that there is no way we can really easily find it out because we don't want our code to depend on it. So it's been hidden. I guess another way to think about this is that information hiding is mostly working and providing us with some modularity, but it's not as straightforward as you think. You really can't rearrange these modules so easily because there usually are some small dependencies and small amount of information which is relevant across the layers.